Okay, we're going to continue on here, and chapter 14, I think, is where we're still at. Uh, Last time we sort of finished up talking about buffers and sort of buffer calculations. So remember that when you have a buffer, really that's a common ion situation, and it's our friend Henderson-Hasselbalch is really what that equation is used for. The pH is equal to the pKa plus the log of the base over the acid, where again the pKa is equal to minus the log of the Ka value. And as we saw, you can use the Henderson-Hasselbalch equation for really any type of buffer situation, be it acidic, basic, or neutral. Um, we also saw the kind of POH version of it, which, as I mentioned a couple of times along the way, you know, most of the time you're looking for pH, so you might as well just go into this equation and sort of get the pH directly. But again, if you want to use the POH version of it, you obviously need to subtract 14 at the end there, usually to get to your pH along the way. One important thing we talked about, which is also going to be very important for what we're going to talk about today, is the idea of when you add volume to volume, you are doing some type of dilution that's essentially happening. And since molarity, again, is moles of solute per liter of solution, as you add volume to volume, that liters of solution is constantly changing or can change. And that means the molarity will change. And one of the things that we saw with buffers, and we definitely will see here as we continue through this chapter, is anytime you are adding volume to volume, the moles remain pretty constant, and or that really doesn't change. So we have to typically do our first sort of ice table in moles. And remember, typically speaking, when we do use moles in an ice table, we oftentimes will not use X since we typically will know kind of what the change is. So we usually will use a number instead of X in terms of the change part of it. As we also talked about, after you do the first ice table, you should convert it back to molarity. And you can convert it back to molarity using the total volume. So volume of whatever you started with and the volume of obviously whatever you added to it. Remember, if it is a good buffer, the pH shouldn't change ginormously, but you should see a change in the pH in the correct direction. So if you are adding acid, you should see the pH go down a little bit. If you're adding base, you should see the pH go up a little bit. Obviously, those are things you want to think about. Any questions on buffers there, what we talked about last time there? All right, then next big topic of the season is everybody's favorite thing, which is titrations. And titrations are oftentimes a technique that is used when a lot of times we have a sort of unknown solution and a solution that is sort of known to us about everything. And we could use titration and the idea of the known solution to figure out things about the unknown solution, like its molarity, its molar mass, those type of things along the way. Um, so when we do a titration, as you're probably familiar with, you use a burette typically. And you could fill the burette with either, for example, an acid-base titration, either the acid or the base could go up there. Typically, you probably have used it with the base up there, but you could put the acid up there if you like. And you have the acid down here, and we slowly add, obviously, one to the other. And we continue to add until we reach what is known as the equivalence point. And the equivalence point in an acid-base titration is the point where exactly the moles of acid will equal the moles of base. So usually sort of considered like in 200A, it's like the end of the reaction. It's over at that point. But that is really the definition of our equivalence point. Our moles of acid in an acid-base titration will equal the moles of the base. So it's that exact point when you do that. That's not to be confused with what is sometimes referred to as the end point in a titration. The endpoint of titration is pretty much what it sounds like. That's the point where you lay up your titration and call it a day. And usually if you're doing a good titration, your endpoint and equivalence point should be pretty close to each other if you're kind of shooting for that good one. But how do we know if or when we should stop our titration? Typically, we use an indicator, and acid-base indicators work over a pH range. The indicators, probably the one you're familiar with is our friend phenolphthalein, right? And phenolphthalein is what color in acidic solutions? It is colorless in acidic solutions. How about neutral solutions? It is still colorless. Basic solutions, it is pink. Yeah, it says pink in basic solutions. And something like phenolphthalein, for example, works over a range of like 8.3 pH to like 10-ish. And at 8.3, it's pretty colorless. And as you progress this way in terms of the pH, you get super dark pink, fuchsia, lovely colors you might have seen when you're titrating, maybe in the previous class as well. You get these really, really dark colors. And we use something like phenolphthalein, for example, in this titration to tell us basically to stop our titration. That's not a bad titration right there in terms of color. I only personally see that when I say extra and credit, the two magical words, and then everybody could get light pink. Before that, nobody could get a light pink titration. So you say those magic two words, then everybody's shoving flask in my face and going, is that light enough for extra credit and stuff, right? So we will talk about, obviously, a couple of things, and one of the things we will talk about is, again, the sort of famous saying that's usually done when most people do a titration, and you might have said it yourself, which is the famous saying of, I only added one drop, and it went from like colorless to super dark pink, right? And we're going to explain, really why that happens. And that's usually a very common thing people say. I just added one drop and it just went super dark pink. So let's talk a little about titrations themselves. We're going to talk about a few different types of titrations, and we're going to talk about sort of how you kind of calculate the pH along the way. So the first titration we're going to talk about really is a strong acid, strong base titration. And what we see here is a titration curve. We got pH on the Y. We have the volume of this case, sodium hydroxide added. This is a titration between hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base. So a strong acid, strong base titration like you did last week. And we will end up with something like sodium chloride, which is our salt. And our friend water here. So just for reference sort of point here, up in the burette in this titration is the sodium hydroxide, and you are adding it to a flask, a beaker of HCl. So you're adding the sodium hydroxide here to the HCl in this case. And this is typically what a titration curve looks like. It's sort of this S-shaped curve. And pretty much on most titration curves, there really is sort of 4 important parts to the titration curve. We're going to talk about those 4 parts right now. So the very first part is actually before you start the titration. So number 1 there is before you start. So before you start titration, before you add, in this case, any sodium hydroxide, that is what we're talking about. The next sort of important part of the titration is after you add 1 drop to just before the equivalence point. That is kind of the second important area of our titration curve. The third part of the titration curve is exactly at the equivalence point. And the fourth part of the titration curve is, even though that indicator maybe changed color, it did not stop you. You just kept going. Why not? And this would obviously be after the equivalence point. So these are sort of the 4 areas of the titration curve. And we're going to talk about how we sort of get the pH at each of these spots and the things that's happening in this type of titration. So let's start with the first spot there, which is before I add any sodium hydroxide. So obviously here, before I add any sodium hydroxide in this particular titration, I have me a flask or a beaker full of hydrochloric acid. And if I wanted the pH of my original solution here, because hydrochloric acid is a strong acid, it's not going to stay together. It is going to completely dissociate apart into H plus and Cl minus. And obviously in this case, that right there is the most important thing. I could get the H plus concentration from it, and I could go directly into our pH equation at this point. So in a titration of a strong acid and strong base, before you actually begin the titration, the only thing you have sitting there again is that strong acid, which means it's basically just a strong acid type problem. And as we talked about, since there's only kind of 6 strong acids, most of them are monoprotic. That means whatever the concentration of the acid is the concentration of the H plus. You can pretty much just go right on into the pH equation at that point. Any questions so far? By the way, this is why when we look at this S curve here, we are starting low in pH because we're starting with an acid, and our pH is rising as we go through the titration because we're adding base to it, right? So we're continuously adding base, and our pH starts to rise. So let's talk about what happens when we actually do start the titration. So let's take a look at step number 2 here. And at step number 2, in this case, once we start the titration, and this is before the equivalence point, we definitely have a reaction that is taking place. So we're adding, in this case, our sodium hydroxide to our hydrochloric acid. So that means I need some type of reaction happening here. So this will be our hydrochloric acid reacting with sodium hydroxide. Again, going to do a double displacement here and make a little bit of water and some sodium chloride in this particular case. Now, in this particular case, since we have started the titration, we do need to do an ice table in this case. And the purpose of the ice table is basically to figure out the effect of adding however much sodium hydroxide we just dumped in there. Now, since I'm adding sodium hydroxide to my HCl, do you think I should do the ice table in molarity or moles in this case? Moles. And you should always do your first ice table in a titration problem in moles, because pretty much in a titration, you're doing nothing but continuously adding volume, right? So you're continuously adding volume as you do the titration. Molarity is continuously changing. So I'm going to do an ice table here. And again, we definitely want to do this one in moles. So we are starting with our HCl once again in the beaker. And we are adding, obviously, our sodium hydroxide to it. So we are adding our sodium hydroxide. So I am going to make up some numbers here just to give you an idea of how to do calculations. So when you ask me later, where did the numbers come from? I just made them up. I'll say that 3 times here in the recording. So these numbers are just made up. So I'm going to start with 4 moles of HCl. Now, because I am at the before the equivalence point, should my moles of sodium hydroxide, which is basically what I am adding here, right? I'm dumping in some sodium hydroxide. Should the moles of sodium hydroxide be less than, equal to, or greater than the moles of my HCl in this case, if I am before the equivalence point? So at the equivalence point, the definition is the moles are equal to each other, right? So if you haven't got to the equivalence point yet, what you're adding is going to be less than that, right? So because we're before the equivalence point where they're equal to each other, and we're adding the sodium hydroxide, the moles of sodium hydroxide at this point should be less than what you started with. And again, I'm just making this number up, which is 2 moles in this case, and obviously we have some zero happening in this reaction. As I mentioned before, a lot of times when we do ice tables with moles, we do not use X. We sort of know the change. At this point in the titration, your sodium hydroxide is like the limiting reagent because you have less moles than you do of the excess reagent in this case, which is your acid. So when we add the sodium hydroxide, all the sodium hydroxide should get used up because you have less of it. And that's going to actually be the change in this case. So our change will be the moles of sodium hydroxide. Once again, you always want to choose the smaller number because if you choose the larger number, you end up with a negative number, and that's not good. At this point, we're just going to finish our ice table here. We got 2 moles of HCl left. We used up all of our sodium hydroxide, and we end up with 2 moles of our sodium chloride. Any questions on the table here? At this point, like I have mentioned before, I would highly recommend that you automatically convert this back into molarity at this point. So I would convert these guys back into molarity by using the total volume. Obviously, in this case, that is the volume of HCl you started with and how much sodium hydroxide you added into it, basically. Yeah? Converted to liters, obviously. And we'll convert this into molarity, and you would also want to convert that into molarity. And I say you should probably just automatically do that because probably 9 times out of 10, you're going to need molarity to continue on. And if you got moles, you're going to probably end up with the wrong answer if you don't adjust it. So at this point, we're still looking for what the pH is. And really, if you're not sure, your ice table can really help you out with hopefully understanding what you have left at this point. So clearly, I got some sodium hydroxide. No, I got some sodium chloride, and I got some hydrochloric acid. By the way, is that a buffer? That is not a buffer because you cannot have a buffer that is a strong acid, right? So again, problematic for a lot of people is I got 2 numbers. I know Henderson-Hasselbalch uses 2 numbers. Let's just try to throw it into that equation. So this is not a buffer. We have 2 things happening here. We have things that we've seen before. That is our friend, the salt, and that is the sodium chloride salt. And that is a neutral salt, right? Sodium from group 1, chloride from HCl, not worrying about it. So really at this point, what we have left is still a strong acid. And at that point, we could get the H plus from it and roll right into our pH equation at this point. So once you add the first drop to before the equivalence point in this type of titration, you do need to do 1 ice table. Really, the whole purpose of the ice table in this case is to figure out what is your new concentration of your strong acid that you're going to have as a result of reacting with the sodium hydroxide. Any questions on that there? All right, so we're now rolling through our titration here, and what is very typical, we're starting to see an increase in our pH, and now what we're actually seeing is a jump to the equivalence point, and there's actually a jump past the equivalence point as well. And let's talk about what this all means. So as we approach the equivalence point, we typically see this sort of vertical jump to it, and then again, a vertical jump after the equivalence point. And this is really because, and the reason why people say that one sentence of, I added 1 drop and it went from colorless to like super dark pink. And that is because my equivalence point is sitting here. And maybe you missed it by a drop, or maybe you went 2 drops too far. But if I'm approaching my equivalence point in this pretty vertical area, does the volume change a lot in that area? does not, right? You can pretty much pick any point you like on this line, and they're all about the same volume, right? But what does change a lot is the pH changes a lot. Yeah. So the pH changes a lot in that vertical area without a lot of volume added, like one drop. And that's important because if you remember again, your indicator works at a pH range of 8.3, for example, to 10, where it is pink. So you could add like one drop or two drops past your equivalence point, and you could actually shoot the pH closer to the 10 range, which would put you right about there. And you will see your solution go super dark pink, right? Even though you're super careful along the way and you only added like one drop, right? And you're like, oh, my teacher down tells me I have to do it again. Anybody? Any teacher tell you like too dark pink, you have to do it again? No, that's good. Truth is, you probably didn't need to do it again if you had somebody that told you that, as long as you were careful. I probably told just the back group there to do it again, but you didn't have to, because if you were really careful and you missed it by one drop or two drops, you're still about the same volume of your equivalence point than you would be if you were at the equivalence point, right? There's really no big difference. The reason sometimes teachers will tell you to redo it again is because if you weren't a really careful titrator like me, and you just open that thing up and waited for pink to happen and shut it off, you could also be way over here and have that same color pink, right? And now, are you near your equivalence point? You're like way far away from your equivalence point at that point. So that's why sometimes teachers will tell you that's too pink, go do it again. But in reality, you don't really need to, as long as you were relatively careful, missed it by a drop or two, everything will still work out well with your calculation. Any questions on that there? All right, so let's talk about actually what happens when we do reach the equivalence point here, which is the third part. So at the equivalence point, we're obviously adding still our sodium hydroxide to our hydrochloric acid. We're going to get our same reaction. And once again, this is what we started with. That is what we're adding. And I'm going to use my made up numbers here, just keep the numbers simple. I'm going to go with 4 moles of HCl. If I'm at the equivalence point, how many moles of sodium hydroxide should I have? At the equivalence point, the moles are equal, right? So we should have 4 moles. Now, this right here is something that you may need to figure out. And what you may need to figure out is how much volume to reach the equivalence point. Sometimes they don't tell you that. They just say, what is the pH at the equivalence point? So there are a couple different ways you could figure out the volume to reach the equivalence point. Perhaps the easiest way would be if it's a one-to-one relationship between like the acid and base. You could use a little M1V1 equals M2V2 action, and you could use your acid and your base molarity there to figure it out. If you want, you would also know the molarity most likely of your sodium hydroxide, which is moles per liter. And since you know the molarity and you know it has to be equal numbers of moles, you could just rearrange the molarity formula and solve for volume and figure out how much you need there. So sometimes, like I said, you will need to sort of do a little calculation to figure out how much volume to reach the equivalence point. The reason you would need that in some titration problems is you'll need the total volume to convert everybody back to molarity at the end. So it's a good way to know that. So here we have 0 for our sodium hydroxide. The good news here is you really hopefully can't pick the wrong number, since there's only one number to choose, and that would be the 4 in this example. 0, 0. We got 4 moles here. Once again, we can use our total volume here and convert back into molarity. And at this point in the titration, once we reach the equivalence point, again, if you're not sure, you can take a look at your ice table to help you out. And again, what we have left is this salt here, right, which is sodium chloride. And as we talked about before, that is a neutral salt, which means when you reach the equivalence point in this titration, your pH should be 7, because the only thing that's left over is a neutral salt that will not go through hydrolysis. And it should always give you a pH of 7 along the way. Any questions on that there? Yeah. To know if it's a neutral salt. So it's like what we talked about when we talked about hydrolysis in the previous chapter. Anything that comes from group 1 or group 2 on the periodic table basically comes from a strong base. So those guys are going to be neutral, like sodium. And anything that comes from either a strong acid or a strong base would be considered its conjugate pair or partner would be weak and not go through hydrolysis and would be neutral. So here, the Cl minus comes from HCl, which is a strong acid. So the Cl minus will not go through hydrolysis and is considered a neutral salt in this case. Yeah. Other questions? By the way, again, it's really a good idea to sort of know where you are in the titration curve. Again, a lot of people just kind of jump in without taking just a moment maybe to think about sort of where you're at. If you think about where you're at, you actually should know, as we'll talk about, what type of calculation you should be doing before you even do the calculation. So that's always much easier than just trying to figure it out as you go. You could also know that again by comparing the moles like we've been doing between what you're adding and what you're starting with. And again, if they're equal, you're at the equivalence point. If whatever you're adding is less moles than what you started with, you're before the equivalence point, and so forth. All right, so back to our curve here. We got 3 parts done. Like I said, the indicator turns super dark pink, doesn't stop you. You keep going because you want the pretty looking curve here. And you continue to add sodium hydroxide past the equivalence point. So let's take a look at what happens in terms of the pH and how we get there when we get to that part. So if we are after the equivalence point, you are still adding, obviously, everybody together. So we're going to have our same reaction. And once again, we're starting with this guy. We are adding this guy. And we're going to start with my 4 made up moles here of HCl. So clearly at this point, I am past the equivalence point. So as we were talking about, when you're before the equivalence point, whatever you're adding is less moles equal to each other at the equivalence point. So as you probably could imagine, if you go past the equivalence point, whatever you're adding is going to be more moles than what you started with, because frankly, you just opened up the burette and let it all drip in, basically. So I'm going to again make up a number of 6 moles for my sodium hydroxide as I'm past the equivalence point, and once again, 0 here. Now, because we are past the equivalence point, there's actually a change that occurs at this point. The HCl now becomes the limiting reagent, since you have less moles of it than you do your excess reagent at this point, which is your sodium hydroxide. So the change in this case is actually going to be our acid, because you have less moles of it. Again, always choose the smaller number. Yeah, minus 4 moles. I say that because there will be a time when you may not want to choose the smaller number, and you should choose it. We come through here, we're going to end up with 0 here. We got 2 moles here. Got 4 moles over here. Once again, our normal, we're going to convert everybody into molarity by dividing by the total volume at this point. And once again, if you're not sure how to get the pH here, you can look at your ice table and see what you have left. And I hope, again, you realize that this is not a buffer. They're not related to each other, right? We obviously have this guy, which is still our neutral salt, which we're not too concerned about. But more importantly, what we got left over now is this guy, which is sodium hydroxide, and that is a strong base. And because that is a strong base, which you would imagine since you're just adding sodium hydroxide at this point to the titration, that's going to get you your OH minus concentration, which will allow you not to calculate the pH, but will allow you to calculate the pOH. And from the pOH, you could then get yourself to the pH at this point. So before the titration begins in this type of titration, strong acid, strong base, you have basically just a strong acid type problem. Before the equivalence point, you have to do one ice table to figure out what is your new concentration of your strong acid. At the equivalence point, you should always have a neutral salt, so it should be neutral or a pH of 7. And past the equivalence point, you have to do an ice table here, again in moles. And the purpose of this ice table is actually to figure out how much of that strong base you dumped in there basically when you stopped. And that will allow you to get your pOH and then into your pH. Any questions on any of those spots along the way here? All right, why don't you try one here? Why don't we do like what is the pH after you add 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar HCl? All right, give it a go. I will as well. We'll see if we get the same answer, hopefully. Okay, let's take a look and see. So once again here, the setup is what we've been talking about. We got sodium hydroxide up in the burette, and we're adding it to our HCl in this case. So we definitely going to need to do an ice table here because obviously we started adding. So let's get some moles here. So our moles of sodium hydroxide, got to convert our volume into liters. So 0.023 liters times the molarity of our base, 0.1 moles per liter. That's going to get us here 0.0023 moles. We'll do the same thing there for our HCl. We have 25 milliliters converted into liters, 0.025 liters. Divide by 1,000, move to decimal point. Molarity here, 0.1 moles per liter, 0.0025 moles. And now we can do our ice table. So it's going to be the same reaction we've been looking at. We're going to take our HCl, going to react with some sodium hydroxide in this case. Again, going to give us our water and our sodium chloride. Again, we are starting with this guy, and we are adding this one here. So initially, we got 0.0025 moles. We got 0.0023 moles, and we got 0. Am I before? Am I at the equivalence point? Am I after the equivalence point? Where am I at? I am before the equivalence point. I know that because what I'm adding is less moles than what I started with. So again, you can use your ice table if you're not sure where you're at in the titration to sort of figure that out. Again, I have less moles what I'm adding than what I started with, so I'm definitely before the equivalence point in this case. Because of that, I know that the change here is going to be our sodium hydroxide, which is what we're adding. So it's the smaller number, 0.0023, 0.0023, and a plus 0.0023 moles in this case. That is going to leave us here with looks like 0.0002 moles, 0 there, and 0.0023 moles at that point. Any questions on the ice table up to here? Yeah. Here, 23 milliliters. Yeah, yeah. Other question? Yeah. Do you have to show the word for salt? You, I'm going to say you should in this case, not for this type of titration, but for some others that we're going to talk about. Sure. So I don't want you just to kind of always ignore the salts because it might actually be important and stuff. So yeah. Other questions? At this point, we do want to just kind of convert everybody back into molarity. So our total volume at this point is we started with 25 milliliters. We added 23 milliliters. That's like 48 milliliters, I think. Yeah. So we're going to divide these guys by 0.048 liters. And that will get us here. It looks like 0.004167 molar and 0.00230 by 0.048. And that's going to give us 0.0479 molar. So once again, we could look at what we got going on here, and we have these two things left. Once again, this is not a buffer situation. This is a salt that we're not going to really worry about. We do have our strong acid, which is this guy, and that means because it's HCl, this would be our H plus concentration. So we're good to go right into our pH minus the log 0.004167. And if we do that minus the log 0.004167, going to get us a pH of 2.38 in this case. Yeah, at this point. See how we did here. I think this was this titration in this table. That's right about between those two numbers, so not too bad. Didn't mess up too bad on that one. In that case. Yeah, so to answer your question again about the salt is, you can sort of ignore it if you want on this particular type of titration, but we're going to talk about some titrations where it will actually play. So again, you just don't want to always sort of ignore it. Okay, yeah. Other questions on this? All right, so again, what we're talking about here is a specific type of titration. This is, again, a strong acid, strong base titration. Specifically, this is how you handle those 4 parts. You should now be able to calculate the pH anywhere along that curve that I choose, or all the points along that curve. That's just your next exam, 600 points along a titration curve. Just calculate it all. All right. The next type of titration we're going to actually talk about is not that one. We just did. We're going to talk about, if it comes, maybe, there you go. We're going to talk about a titration of a weak acid and a strong base. So for example, something like acetic acid, which is a weak acid, plus sodium hydroxide, which is a strong base. So this is a weak acid, strong base titration. Again, the setup here is very similar. We're going to have our sodium hydroxide up in the burette, and we're going to add it to our acetic acid in the beaker or the flask. We do see a similar type of titration curve here, this sort of S curve. It does start perhaps a little higher than the other one because it's a weak acid. But there is also still the same 4 parts to this titration curve. There again is before we start the titration. There is once you start the titration to before the equivalence point. There is again at the equivalence point. And once again, just like the last one, there is past the equivalence point. So again, we're going to kind of look at each of these steps along the way and how you should handle the pH calculation. So let's take a look here and see. We'll start with the very first part, which is before the titration begins. So once again, before the titration begins, in this particular case, you have just a weak acid present. So if I want the pH of a weak acid, this is a calculation we've done in the previous chapter. This is really just a Ka type problem of a weak acid. So you would take your acetic acid here, do a little dissociation of it. You would obviously do an ice table here. This ice table you can do with the original molarity of the acid because you have not added anything at this point. So there is no volume changing at this point. So whatever the molarity of that weak acid is, you can do it. This is going to be a regular old, good old fashioned zeros and some X's throwback type of table here. And do our molarity minus X, X, and X. Obviously, this is going to go into our Ka expression. And that's going to equal the Ka value of like 1.8 times 10 to the minus 5 for acetic acid. Obviously, here we're going to solve for X. You could do an assumption, maybe a quadratic. Most likely an assumption might be okay. But you definitely want to check it. When you solve for X, that will equal the H plus concentration, and then you could go into your pH formula at that point. So you can see in this titration, it is a little bit different than the previous type of titration where you have a strong acid, you can just go right into the pH equation. Here, because you're starting with a weak acid, you need to do a one ice table, a Ka type problem calculation to get your X value, and then obviously get your pH from it. Any questions on that there? All right. Then let's talk about what happens here. We can see again, our pH is starting to rise as we're adding. So let's talk about what happens when we're in the second area here, which is before the equivalence point. So if we take a look here, before the equivalence point, we have definitely added. So in this case, we will get the reaction that's going to happen, which in this example is acetic acid plus some sodium hydroxide. Going to do a little double displacement reaction here, make a little sodium acetate and some water in this case, right? And once again here, this is what we are starting with in the beaker. This is what we are adding. So again, we got our sodium hydroxide adding to our acid in this case. Once again, because we are adding volume, we need to do this ice table in moles. So I'm going to use my made up moles again. So I'm going to go with 4 moles of my acetic acid that I'm starting with. Once again here, because we are before the equivalence point, the moles are not equal to each other. We're getting up to that point. So the moles of what we're adding is going to be less than what we started with. So again, just making up a number here, we'll go with 2. And we will have 0. Once again, because we are before the equivalence point, whatever we're adding is the limiting reagent going to get used up because, frankly, it's a smaller number and you have less moles of it. So the change here is going to be minus 2 moles, minus 2 moles, and a plus 2 moles. That means at equilibrium, we got 2 moles here, 0, and 2 moles here. First off, any questions on the ice table here? At this point, like normal, we're going to take the total volume here, and we're going to convert these guys back into molarity. And again, at this point, if you're not sure sort of what's going on or what you have left, you should really look at your ice table because it does have a lot of information. I got myself some sodium acetate left, and I got myself some acetic acid left. What is that? That is are those things related to each other? This is a weak acid, and dare I say that is the salt of its conjugate base. That is also known as a buffer. Yeah. So you just made a buffer here in this titration of a reaction of a strong base with a weak acid has actually formed a buffer at this point. And that is what happens in this type of titration as you start the titration to before the equivalence point. you will actually make a buffer. This also illustrates the fact that you can actually make a buffer from this type of reaction, a reaction of a strong base with a weak acid, but the buffer itself is not the strong base. It's gone, as you can see here from the table. What it leaves over at the end of that reaction is actually the buffer. And because this is a buffer, this is where we could use our friend, right, Henderson-Hasselbalch here to grab ourselves the pH. Alternative to that, if you don't want to use Henderson-Hasselbalch, you could do a second ice table where it would be like a buffer ice table where you could do, if you wanted to, acetic acid dissociating into H plus and acetate. The key on this, if you choose an ice table and not the Henderson-Hasselbalch, like we talked about when we were doing buffers, you should have a molarity here, and you need definitely a molarity there. Yes, otherwise, again, you're not doing a buffer, you're just doing like the weak acid. So probably Henderson-Hasselbalch a little less room for error at this point, but you can still roll with the ice table like we talked about with buffers if you want to do it without the Henderson-Hasselbalch in this case. Obviously, the pKa would come from the Ka of our weak acid that would be given to us in the problem in this case. So very different than what happened in the previous type of titration where we just had like a strong acid left over. Here you will form a buffer. And that is why you will see, for the most part, as you're coming through this area, you will make a buffer. pH will kind of maintain. Then all of a sudden, you get that jump upwards to the equivalence point. And that is because as you're doing this titration, you make a buffer, and then you gradually using up your buffer. We talked about buffer capacity, right? At some point, if you keep adding base, you're going to blow through the acid part of the buffer, and that's what happens here. And then you get that really kind of big jump in pH that occurs to the equivalence point, and then you get another jump afterwards as well. So you kind of make the buffer, and then you kind of blow through the buffer as you continue your titration, and then you'll usually see that pretty good jump in pH to the equivalence point. Any questions on that there? All right, then let's talk about what happens here at the equivalence point. So that is the third step there, which is the equivalence point. And once again, we still have our reaction of, in this case, our acetic acid, which is our weak acid, plus our sodium hydroxide, which is our strong base. Going to make our sodium acetate and our water in this case. And once again, we're starting with this guy, and we are adding this guy. So initially here, again, with my made up 4 moles, because we are at the equivalence point, again, the definition is the moles are equal to each other at this point. We will definitely have an equal amount of moles of our sodium hydroxide, and we'll have nothing here. Once again, you hopefully can't pick the wrong thing. There's only one number, so 4 moles, and plus 4 moles here. That is going to get us here at the equivalence point, 0, 0, and 4 moles left over, which, like everything else, we will convert back into molarity using our total volume at this point. There's any questions on the ice table here? Just like we saw in the previous titration, what we got left over is sodium acetate, and that once again is a salt. So whenever we have a salt that is present, the one thing we have to think about is, will this salt go through hydrolysis, right? Will it react with water and produce H3O+? Will it produce hydroxide? So that is the question. Will this salt go through hydrolysis? This salt is sodium acetate, which is going to break apart into a sodium ion and an acetate ion. We know hopefully sodium is group 1, comes from sodium hydroxide, which is a strong base, which means it's going to be neutral. How about my acetate? Where does it come from? I'm going to say that acid right there, which would be acetic acid, yes? And acetic acid in this case is a weak acid, which means this is going to be a relatively strong conjugate base and will go through hydrolysis here. So this salt is not going to produce a pH of 7 in this case because it is not a neutral salt, but it will continue to react, and it's going to continue to react with our friend water that's sitting there with it. And that means at the equivalence point in this type of titration, you got to do not one ice table, but you get to roll the dice and do 2 ice tables. Yes. And the second ice table is a hydrolysis ice table. So because it comes from a weak acid, this will be the conjugate base, which means it's going to act as a base when it reacts with water, and it's going to accept the H+. The good news is it will always form where it came from. You probably have that in the problem. So it will always form where it came from, and it will make a little hydroxide action. So before I even do this ice table, the pH here at the equivalence point should be acidic, basic, or neutral. Should be basic. Yeah, we're forming hydroxide here. So we should have a basic pH in this type of titration because of the salt going through hydrolysis. This is going to be an ice table where you take the molarity from your first table and you put it into your second table as your initial. This is also why you need molarity, because if you do this in moles, most likely you will end up with the wrong answer if you don't adjust at the end. So might as well just put it back into molarity at this point. This is going to be a 0-0 type of ice table with some X's at this point, since we're kind of doing molarity again. And that'll be our initial minus X, X, and X. This is going to go into our K expression here of our products. Over our reactants. By the way, this would be a K, A, B, C, D, F, G. This is going to be a K, K, B, because again, I got hydroxide here. You could probably imagine in this problem, you will not be given the Kb value. You most likely will have the Ka value given to you for the weak acid. So this is, again, a throwback move. We could use our Kw, right, to calculate the Kb value. You most likely will have to do that. Here you're going to solve for X. It also should remind you that X in this case is not the H plus concentration. It is the OH minus concentration. So you're going to get the OH minus concentration, which means you're going to go POH first and then pH. Yeah. So again, a little bit more complicated, perhaps, than the last titration where you just really have a pH of 7 at the equivalence point. Here, because we do have the salt that can go through hydrolysis and will go through hydrolysis, it requires 2 ice tables. Again, the purpose really of the first ice table is to figure out the concentration of your salt. And then the second ice table is the hydrolysis one, like we did in the previous chapter. So to go back to the earlier question about the salt, again, this you want to make sure you kind of understand the salt that you're dealing with, because as you can see here, it can definitely affect the pH of the solution in this case. Yeah. Other questions? All right. So we do have a basic pH. As you can see here, they got like an 8.72. And now we're going to talk about the fourth part here where we blow past the equivalence point and we continue to add some sodium hydroxide. And if we do that there, we're now going to be past the equivalence point. Still going to get our same reaction, our acetic acid plus our sodium hydroxide, making our sodium acetate and our water in this case. Once again, we're starting with this guy. We are adding this guy. So initially starting with our 4 moles of our acid, Again, because we are past the equivalence point or after the equivalence point, we now know they're no longer equal, and we're continuing to add our base. So we're going to end up with more moles of our sodium hydroxide than we started with our acid, and that'll just take 6 as a made-up number, and we'll go 0. At this point, we get again a shift to what happens because we have less moles of our acid at this point in the titration. It's going to be the limiting reagent. Our sodium hydroxide here will be the excess reagent, and this is going to be -4 moles, which is our acid. Again, always take the smaller number. We're going to end up with 0, 2 moles here, and 4 moles here. Once again, gonna just automatic convert back into molarity using our total volume. And at this point, we want to think about what we got left, so we can use our ice table to help us. We got a little sodium acetate and sodium hydroxide. Is that a buffer? That is not a buffer, although most people, again, when they see 2 numbers, just jump and throw it into that equation. Those are not a buffer. This is obviously a salt that will go through hydrolysis, like we just saw at the equivalence point. And it's really a conjugate base, like we just talked about. And we also have sodium hydroxide, which is a strong base, right? So what we have left at this point in the titration after the equivalence point is essentially 2 bases. And between those 2 bases, the stronger base is definitely the sodium hydroxide. It is going to be probably the major contributor to the pH because, frankly, you have it in your burette. You're just dropping it into the solution. As soon as it hits the solution, it's going to produce hydroxide really quickly. That's all it has to do, basically. The salt over there has got to go find some water, do a little reaction to produce the hydroxide. So although it is producing hydroxide, your major production of hydroxide is going to come from that strong base. So we typically, at this point in the titration, we ignore the contribution of the salt in terms of the pH because the sodium hydroxide is going to be the major contributor. That means that we basically have at this point the hydroxide concentration, which will allow us to get to the POH and again get to the pH at this point. So past the equivalence point in this type of titration, again, you're just unloading your sodium hydroxide in there. You need to do 1 ice table basically to figure out how much sodium hydroxide you got left after you dumped it in there. And from that, you can get the hydroxide concentration and then obviously get yourself to the pH. Question on that there. All right. So there are these 4 distinct points in this titration, which is a little bit different than obviously the titration we talked about previously. Also, why it's really important to kind of know where you are in the titration curve, because if you do, you should know what type of problem you're doing. If you're at the beginning, you should be doing a Ka problem. If you're in the before the equivalence point, you should be doing a buffer problem. If you're at the equivalence point, you should be doing a hydrolysis problem. And if you're past the equivalence point, you basically should be doing a strong base problem. These are all problems that we've calculated previous to this part. The key and trouble most people have is not knowing where to do it or where they're at or what they're doing. So again, sometimes it's a really good idea to just take a moment and try to figure out where you're at because you should know what type of titrate calculation you should be doing. And that makes obviously the calculation a little bit easier. Why don't we try one here? Why don't we do let's do all right, what is the what is the pH after you add let's do 27 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar acetic acid, Ka for acetic acid, 1.8 times 10 to the minus 5. All right, so see what you come up with here. So we'll start with our reaction here. Our acetic acid reacting with our sodium hydroxide. Again, making our sodium acetate here on the double displacement and our water. Once again, obviously, since we are adding, we're going to do our ice table here in moles. So we are starting with this guy here. We are adding this one here. So again, converting our volume into liters, 0.025 liters for our 25 milliliters times 0.1 gives us 0.0025 moles to start with. For our sodium hydroxide, also converted 27 milliliters into liters, divided by 1,000, 0.027 times 0.1, going to get us 0.0027 moles and 0 here. At this point, you should be able to recognize that you have more moles of what you're adding than what you're starting with. So you are after the equivalence point for sure because of that. That also should tell you that we're going to have that switch we've been talking about, that in this case, because the acid now has less moles than the base, the acid is going to be the limiting reagent, and also our change in this case, 0.0025 minus 0.0025 and plus 0.0025 moles. That's going to get us at equilibrium here, 0. We're going to go that minus 0.025, 0.0002 moles, and 0.0025 moles here. Converting back into liters, so we got here 25 milliliters of acid we started with. We added 27 milliliters. So that's going to give us a total volume here of 52 milliliters. We're going to divide that obviously into liters, so 0.052 liters for both of these. And we will end up again at this point with 0.00385 molar and 0.0025 divided by 0.0520. That is 0.04807, we'll call it. At this point, you have this guy left over and this one. Once again, this is not a buffer, but we do have a salt that will go through hydrolysis. And we also have, again, our sodium hydroxide, which is a strong base. As we know, because we know we're after the equivalence point, we always are going to ignore the contribution of the salt at this point. We are going to look at the strong base as our major contributor. That means that this should be our hydroxide concentration. And that means we could calculate the pOH minus the log of 0.00385, it looks like. Minus the log. Log. Going to get you a 2.41 on the pOH. Again, if for some reason you thought that was the pH value, it should not make sense to you because you're definitely at the end of your titration and you're dumping nothing but base in there. So you should have a basic pH. So pH a little 14 minus that there should bring us into a basic pH of about 1159, which is definitely basic in this particular case. Question on that there. So we can see how we did. That's probably between those, yeah. Before 28, yeah, not too bad. Since that is the titration, it is not too bad. Any questions on this type of titration? So again, kind of 4 different types of problems that we've done previously. the key and where people again struggle is recognizing where they're at and what type of problem. So don't be afraid to take a moment to think about where you're at so you know what type of problem to do. Even if you can't do that, don't be afraid to look at your ice table and see what you got left over, what's happening, and that gives you a lot of pieces of information. Any questions? All right, relay it up.